So I'm going to leave that one up there for now as well. The technology gap. I mean, I think John might have mentioned technology gap the other day as well. We don't have all the solutions. We don't have all the answers. This is where research and development comes in. And of course, my little plug for green chemistry education on the bottom. This is why it's so important. This is why we need our scientists thinking about this right at the very beginnings of their education, so they can start filling this technology gap. And I'll bring up John's toolbox as well, just to reiterate this. So in chemistry, we can pretty much make anything if we can think of it. If we can draw a structure that doesn't defy any laws, we can make it, and we have all these tools in the toolbox to make these molecules. But what we might not have is a greener alternative in that toolbox to actually make that molecule. So, we estimate that the greener alternative toolbox might be, 80 to 90% empty. And of course, that's a very rough estimate. So that really needs to be filled so that we have more tools in our portfolio to design these alternatives. So this last one I'll mention, insisting on perfection. And we do insist on perfection, and we should insist on perfection. There's no question on that. What do I mean by that? It's an interesting scenario when you get up and speak about green chemistry and you're talking about your process, and you might be talking about your whole process and the steps that you took to actually green your process. And a lot of times when we're talking about this, we're even more heavily criticized by our colleagues or others who say, well, geez, you missed something over here, and you missed something over here. And yes, it's not perfect. And so this is where we reiterate that green chemistry is a process. And this is where incrementalism versus perfection comes in. It's a process, and I liken it to the runner who always is trying to run. They're always trying to run a faster and faster mile. We're sort of aiming towards a 0-minute mile. But are we ever going to get to a 0-minute mile? It's pretty difficult. So, all we can do is drive closer and closer to that goal. So, if we think about these barriers that we do come across in the implementation of green chemistry within an industrial setting, I then want you to think about, well, what is it in the chemical industry? What are the characteristics of the chemical industry? If you have a look at the general characteristics of the chemical industry, you'll notice a number of things on these bullets, but you'll see, look at that, capital intensity and economies of scale. You'll see strong regulation. You'll see high research and development expenses. All of these barriers, so-called barriers that I explained to you in a couple slides ago, are really just general characteristics of the chemical industry itself. It's not unique to green chemistry. All of these industrial sectors face it. These economies of scale and capital intensity, it's a very, since we can scale up and manufacture these things on such a large scale, it will be capital intensive, which will bring down our labor costs for the manufacturing. So it is what the chemical industry is all about. Strong regulation, which is a good thing, but there is strong regulation in chemical industry, so those regulatory barriers are going to be there. High research and development expenses. If you're in the pharmaceutical industry, you know that that sector has some of the highest research and development expenses. Because we are designing the next generation of material for the current generation. So all of these things that are perceived as barriers, really just characteristics of the chemical industry. So I'm getting to my third and last phase here, which is to think about the future. So we have this education, implementation, but how will we advance green chemistry throughout the 21st century? And of course, it'll take multiple things, including research and development, which will lead to implementation and manufacturing and industrialization. Education, of course, teaching that next generation of scientists how to design those greener alternatives. And then we need tools. We need the right tools to help us design these alternatives. We need them both in a classroom setting and in a research and industrial setting. So to think about this a little bit more, as was mentioned, I was a research scientist at Roman Haas Electronic Materials, and some of my research involved the synthesis of silicon-based polymers for optical electronic waveguide materials. And these waveguide materials were used in backplanes in circuit boards, in electronics, and also as touchscreen surfaces, the surfaces on touchscreens and things like that. And we would, in our group meetings, we would have intense group meetings where we were going through our design criteria for these polymers that I was making. I was making new materials. And these were our design criteria. We had actually several others, but I simplified them a bit. It had to have a certain solubility because we were actually coating it onto a surface. It had to have a certain melting point and glass transition temperature. If this is a PDA handheld device, it had to have those correct thermal properties so that it wouldn't warp or disform in a hot climate. It had to have certain mechanical properties. So it had to have the correct tensile strength and modulus, something that could have a little bit of give and flexibility to it, but yet be strong enough and flexible enough to not be brittle and break over its lifetime. It had to have a certain refractive index. Since we are bending light, it's a waveguide material, so it had to have a very specific refractive index. It had to have a certain surface tension, so you don't want it beating up on your surface as you're coating it onto your substrate. Many times, until I got there, what doesn't come up in these group meetings discussion is, well, what about the toxicity? What about the environmental hazard? What about the impact? Aren't those physical properties of that material? And just as if I made something that didn't have the correct thermal properties or mechanical properties and did get brittle and break as I used it over its lifetime, I would think that would be a design flaw, and I would go back and I would redesign and make a new material and design it out of that process. Shouldn't toxicity and environmental impact also be considered a design flaw? And if that product, if that material exhibits toxicity and environmental impact, we can go back and design it out and redesign our process. So many times in our meetings, in industry, and perhaps you can attest to this as well, we don't think of these as criteria in our design. And this is what green chemistry really is all about, thinking about it in our design phase. So, as another example, as a great example is, we have a group meeting about we want to make a non-stick surface. I mean, if you think about the first group meetings about how do we design a non-stick surface, well, okay, now we know there are many, many properties that we look for in a molecule and a material that will exhibit those. We have this fluorinated carbon chain here that will have a nice non-stick surface. So the very intent of that original Teflon pan or non-stick surface was to be a non-stick surface. The fact that molecule might also exhibit some toxicity, might be persistent in the environment, build up in our bodies and our ecosystems, that was not part of the design criteria. That was kept separate. Just as on the left, a red dye that might also cause cancer, the function of that material was to be a red dye. It was a red molecule that we might have built into our systems to not oxidize in the air or the light, and to have these performance criteria. Just as bisphenol A, which we had a great talk by Pete Myers yesterday about this one chemical that's really entering into our lives, or is in our lives. Bisphenol A on the left, it's a component of polycarbonate plastics. So if you know what a polycarbonate plastic is, it's a shatterproof plastic. Really, it's in and it was a great replacement for our eyeglasses to replace glass that was actually heavy on your face. It's a great replacement. And its intent and its design was, not to be an endocrine disruptor. That's a unintended consequence of our design. Lead, lead in white paint is a whitening agent, it's a stabilizer, it's an anti-knocking agent in our gasoline to make our cars run better. Now, that was the original intent, not